Hello everyone, welcome to Sai Tutorials Jamkandi. Uh, in our tutorials, 10th class Kannada medium, English medium, maths, science, English classes are available in regular classes as well as in online classes. So please join us and learn things. So dear students, in this session, I'm going to discuss about the third chapter of the second PUC physics chapter, that is current electricity. So in the previous session, I have discussed about the basic concept related to the current electricity, what is current and how the electricity will produced, and what are the charge carriers, how they will going to happen. And in today's session, uh, let us discuss about current density, that is denoted as J. Okay. In this today's session, let us discuss about current density, that is J. See, if a current I is uniformly distributed over an surface S is perpendicular to it, then it is denoted as, that is J is equal to I divided by S. Suppose here it is a type of conductor, okay, that is denoted as P, which is having the surface area yes, okay, which is having the surface area yes. So the current is equal to the, here the net current is equal to the net charge flowing per unit time or per unit second, per unit time in second, it is called as current, that is net current. Now the current density, the current density, what is current density? The surface area is like this, okay, yes. If a current is I, if a current I is uniformly distributed over this surface area, these are the pointed lines are there, no? These are current is uniformly distributed over the surface, yes, and is perpendicular to it. How it will be produced? It is moving perpendicular to the surface of that conductor, okay. See, therefore, it is denoted as the total current passing per unit surface. Yes, it is called as a current density. It is called as a current density. Now, current density, it is a vector quantity. Okay, it is a vector quantity because it is having the magnitude as well as the direction. See, the direction of a current density is same as that of the direction of motion of positive charges. See, the current density, whatever the direction that is of current density is there, no, it is same as the direction of motion of positive charges. How the motion of positive charges will takes place, no, in the same way the direction of current density will happen. Now the SI unit of current density is ampere per meter square, ampere per meter square, because the SI unit for current is ampere and the SI unit for surface area, that is meter square. So the SI unit of current density, that is equal to ampere per meter square. Now the relation between current and current density, okay, the relation between current and current density. So we can see the relation between current and current density. I have the formula like this. Suppose if I want the current only, it will become J into S. So to do this, we need to make integration of the smaller part of the surface area having, for a smaller surface ds having the current, that is dI. If you make the line integral over that small surface ds, which is having the current di, then it is equal to the line integral of di, that is current is equal to the line integral of current, that is di is equal to the line integral of the surface yes, and this is small j into the surface small surface area, that is eds, over a fine surface area, that is s. Okay, this is the concept related to the current density. See, if I consider any conductor, or if I consider any type of the material that will conduct the electricity, if current I is uniformly distributed over an surface area that is S and perpendicular to it, see the current will move in a perpendicular direction to that surface, so then it J will become the total current present, I mean the total current passing through that surface area to the surface that is yes, surface area that is yes. So current density is a vector quantity because it is having the magnitude as well as the direction. Now the direction of current density is same as that of the motion of, okay, direction of motion of the positive charges, I mean in which direction the positive charges are moving, in the same direction current density is also same. Now the SI unit of current density, that is ampere per meter square, ampere per meter square. Now relation between current and current density, that is equal to line integral of the small surface ds, though, so that the current flowing through that small surface ds is equal to the line integral of the small current passing through that surface ds, that is equal to line integral over the surface s into j, that is current density into the small distance whatever we have taken over a finite area, that is s. Okay, this is the current density that is denoted by the letter J bar, which is having the vector quantity. That's why I have written bar over the current density, that is J. Okay. So after knowing this concept, let us know about what is drifting. Okay, drift velocity of free electrons. What do you mean by drifting then? See, drift velocity. So before going to discuss, let me consider a small example. I mean, okay, drift velocity. Drift velocity. What do you mean by drift velocity? See, it is defined as the average velocity. It is defined as a average velocity with which free electrons in a conductor get drifted in a direction opposite to the direction of the applied electric field. Okay, see, drift velocity. So let me consider any kind of conductor. Okay, let's wait a second. Any type of conductor here. It is a conductor. This is having positive charge and this is having negative charge. Okay. Now, suppose the electric field E bar will be in this direction. E bar will be in this direction. Now, so whatever the free electrons present in a conductor get drifted. Okay, these will get drifted. It may go like this. Okay, in a zigzag fashion. But those free electrons in a conductor get drifted in a direction opposite to the direction of, I mean opposite in the sense like this, opposite to the applied electric field like this. Okay, see, the drift velocity is defined as the average velocity. It is defined as the average velocity with which free electrons in a conductor get drifted in a direction opposite to the direction of the applied electric field. So let me write here. It is defined as the, please note down, defined as the average velocity average velocity with which, please note down, with which these free electrons, whatever the free electrons in a conductor get drifted. Okay, get drifted in which direction? In a direction opposite to the applied electric field. Opposite to the applied electric field. Okay, it is defined as the average velocity with which free electrons in a conductor get drifted in a direction opposite to the applied electric field. Okay, this is the concept. Now, how to derive the drift velocity? I have considered an electric field in a conductor in the direction from positive to negative. But the free electrons, the movement of or the motion of electrons or the motion of free electrons inside that conductor will be the opposite to the direction of the applied electric field. Therefore, the force experienced by a free electron. Now the force, whatever the force experienced by a free electron in conductor is given by, that is, F bar is equal to free electrons E opposite to the applied electric field. It is denoted as negative. This is equation number 1. So negative sign shows that the direction of force and electric field are opposite to each other. Now the acceleration produced in the electron. Okay. Now the acceleration. So whatever the here the acceleration. Okay. Here the acceleration produced in the electron is given by acceleration, that is F divided by m. F bar. We know that from Newton's second law, that is F is equal to ma. Therefore, acceleration produced in the electron is given by a bar is equal to F bar divided by m, where m is the mass of that electron. If you substitute what is the value of F here, that is minus E divided by E into m divided by m. This is equation number 2. Okay. See, whatever the acceleration that produced inside the electron will lasts, that will remain for a short time. Okay, that will remain for a short time. So these accelerated electrons collide with the vibrating ions of the conductor. See, if there is a conductor, if you apply the electricity to that conductor, the number of free electrons will produce inside that conductor. I have told you. Okay. See, if I considered an conductor, the number of if you produce the electricity to pass through that conductor, there will be a number of free electrons will move inside that conductor. Okay, move inside that conductor. But that accelerated electron will collide with the vibrating ions of the conductor. The other ions that will collide with the other ions. So the small interval of time between the successive collision between the electron and the ion in the conductor is called as a relaxation time. See, I told you that in a conductor, okay, in a conductor, there are so many number of electrons, I mean free electrons will takes place, okay. So if you apply the electric field to pass through them, the free electrons, the whatever the free electrons present inside that conductor will collide with each other. They will get accelerated and they will get accelerated and collide with each other. Okay, collide with each other. So whatever the time, okay, whatever the time taken to collide, okay, whatever the time, that small interval of time between the two successive collision. So if suppose if two electrons will collide each other, the time interval between the two successive collision between the electron and ion in the conductor is called as a relaxation time. Relaxation time. Now the electron accelerates for an average interval of time tau. If you consider the time, that is tau, relaxation time, that is tau. Now the drift velocity that is in form of vector is given by u plus a bar into tau. From the physical kinematics we can write this. So whatever the initial velocity, that will become 0. So this is a tau. Now we have derived the acceleration produced in the electron, that is a bar. A bar is equal to what is a bar from equation number 2? From equation number 2. Okay, from equation number 2, that is acceleration produced in the electron, that is equal to minus small e into capital E divided by, yeah, okay. If you substitute Vd, if you substitute A in equation number 3, I mean let us consider this as equation number 3, okay. If you substitute in that equation, you will get, see, that is Vd bar is equal to minus Ee bar divided by m into tau. This is the equation for drift velocity, or in the magnitude, that is Vd is equal to E tau divided by m. Divided by yeah, this is the equation for drift velocity. This is the equation for drift velocity. See, average drift velocity. What do you mean by drift velocity? It is defined as a average velocity with which the free electrons in a conductor get drifted in a direction opposite to the applied electric field. Okay. Applied electric field. Now, the force experienced by a free electron in a conductor is given by F is equal to minus E into capital E bar, that is electric field. Here, the acceleration produced in the electron, that is A bar, is equal to F bar divided by M. So, what do you mean by F here? That is, if you substitute equation number 1 in equation number 2, acceleration, that will get minus small e into capital E bar divided by M. Okay. Now accelerated, okay, the electrons will get accelerated and collide with each other, and whatever the ions present in that conductor will collide each other. So the time interval between the two successive collision is called as a relaxation time. Now if you consider the average velocity, average drifted velocity, that is equal to, according to physical kinematics, that is u plus at. So if you substitute in the vector form, that is u bar plus a bar into tau, or if you the initial velocity, that is equal to 0, the remaining, that is a bar into tau. This is equation number 3. So if you substitute a bar value in this equation, we will get the drift velocity. We will get the drift velocity, that is equal to small e into capital E into tau divided by m. This is the equation for drift velocity. Okay, this is the drift velocity. Here small e. Okay, here we have derived this expression. Is it or not? We have derived the expression for drift velocity. So where E is the charge on the electron, m is the mass of the electron, and capital E is a electric field, tau is a relaxation time. What I have said you, what is tau? What is tau is relaxation time. The time interval between the two successive collision between the two ions is called as a relaxation time. Now, the random speed of the free electrons in a metallic conductor depends on the temperature you apply there. See, the movement of free electrons, in the conductor will takes place, which will be depends on the temperature, and it is of the average order of 10 to the power of 6 meter per second. The drift speed of free electrons is of the order of 10 to the power of minus 4 meter per second. 10 to the power of minus 4 meter per second. The average velocity is like that. The drift speed of the free electrons is equal to the 10 to the power of minus 4 meter per second. Now, this is all about the drift velocity of free electrons. Okay. So, I have said you that what is relaxation time. Okay. Relaxation time and mean free path. Okay. The average time elapsed between two successive collisions of a free electron with a metal ions, the collision between the electron and the ions in a conductor is called as a relaxation time. I have said you, it is denoted by the letter that is tau. The average distance traveled by an electron between two successive collisions is called as a mean free path. It is denoted by the letter lambda. Okay. See, the average time elapsed between two successive collisions between the electron and the ions present in a conductor, it is called as a relaxation time. It is denoted by tau. Now, the average distance traveled by an electron between the two successive collisions, the average, whatever the distance traveled by an electron between the two successive collisions is called as a mean free path. It is denoted by the letter that is lambda. Okay, this is all about the drift velocity and related concept. Okay, now coming to the concept that is mobility. Okay, very important concept, that is mobility. So let me change the pen. Okay. See, in a general sense, mobility means movement. Okay. In the general sense, mobility means movement. But in physical quantity, what do you mean by mobility? It is denoted by the letter that is mu. Okay. It is denoted by the letter that is mu. So what do you mean by mobility? See, here I have derived drift velocity, that is defined as Vd, and this is E is electric field. So can we say that mobility of a current carrier, is it the ratio of drift velocity to of the current carrier in a material to the applied electric field? Is it or not? Okay, it is the ratio of drift velocity of the current carrier in a material to the applied electric field. Applied electric field, that is E, and it is across that material, it is called as a mobility. Okay, the mobility of electrons and conductivity of a material are related by the expression that is sigma. That is sigma is equal to Ne nu for a metallic conductor. What is this? What is this? The mobility of electrons and conductivity of a material. So, conductivity of the material will takes place when it will be takes place, the mobility of the electrons. Okay, the movement of the electrons, the motion of the electrons will takes place. Then only the conductivity of materials will takes place. Okay, these are related by the expression that is sigma is equal to Ne, number of electrons, and nu, that is mobility. Is it or not? Okay, the metallic conductor sigma, that is sigma is equal to electrons and holes for a semiconductor. For a semiconductor. In semiconductor, what will happen? That is number of electrons as well as number of holes present in a semiconductor, where when E is the electron density, NH is the hole density, and UE is the electron mobility, and UH is the hole mobility. This is all about the concept, that is mobility. It is a ratio of drift velocity Vd of the current carrier in a material to the applied electric field E across the material, that is nu is equal to Vd divided by E. So where Vd is equal to, what is Vd? E small e capital E tau divided by m. Okay. See, if we know that, for further information, let me write nu mobility is equal to Vd divided by E. Is it or not? So what is Vd here? We know that it is m into whatever left. So here E get cancelled. What is left here? That is E into tau divided by m. This is the expression for mobility of the current carrier. Mobility of the current carrier. Okay. Is it or not? Is it right or not? Okay. Here N is a electron density, NH is a hole density. If you take, for example, semiconductor. For semiconductor, that is related by the expression mobility of the electrons and conductivity of the material are related by the expression, that is sigma. That is sigma is equal to Ne into nu for a metallic conductor. Now, this is all about the mobility. This is all about the mobility. Now, please note down. So, the next important concept that is related to your syllabus, that is expression for current and current density in terms of that drift speed. Okay, in terms of that drift speed. So if you know the what is drift velocity and drift, what do you mean by drift velocity and all? So we can derive many expressions. Okay, so in the same way, that is expression for current and current density. For further information, expression for current and current density in terms of drift speed. Okay, in terms of drift speed. Suppose we know that electric current. Okay, electric current is equal to how much? That is I is equal to N into A into E into Vd. Okay, this is equation number 1, and J is equal to Ne into Vd. This is equation number 2. Okay, suppose can I write that current is equal to the A into J bar? Is it or not? A into J bar. This is the relation. This is the relation for current and current density in terms of drift speed, where N is the number of electrons per unit volume of a metallic conductor of cross-sectional area, that is A, and E is the charge on the electron. This is the expression for current and current density in terms of drift speed. So before coming to this concept, let me discuss something new. Okay. most important concept, that is Ohm's law. Okay. So what does this indicate? See, according to Ohm's law, so whatever the current, whatever the current flowing through the conductor, okay. Suppose if you consider any conductor, the current I flowing through a conductor, it is directly proportional to the potential difference V across the, let me state, okay. According to this law, the current, please note down, the current I, flowing through a conductor is directly proportional to the potential difference that is denoted by the letter, that is capital V, across, please note down, across the ends of the conductor conductor, it is called as a Ohm's law, but it is having some kind of condition. So whatever the physical conditions, what are the physical conditions to be happen here is like temperature, pressure, strain, etc. of the conductor remains unchanged. Okay, this is the condition here. So in simple way, Ohm's law can be written as, according to Ohm's law, the current I flowing through the conductor is directly proportional to the potential difference capital V across the ends of the conductor, that is denoted by the current I is directly proportional to the potential difference, that is V. This is equation number 1. Okay, this is equation number 1. So that is I is directly proportional to V. This is equation number 1 according to Ohm's law. Now, if I want to remove this proportionality constant, I will write, or I can also write, see, so if current I is proportional to the potential difference, so can I write this potential difference is also directly proportional to that current? Is it or not? Okay, if current flowing through that conductor is directly proportional to the capital V, so can I write that potential difference is also proportional to the current I? Is it or not? So this is equation number 2. Okay. If I want to remove this proportionality constant, can I write V is equal to R into I? This is equation number 3. This is V is equal to R into I, where R is called as a proportionality constant. Which constant? Proportionality constant. Proportionality constant, that is electric resistance. Okay, electric resistance, please note down, that is electric resistance. So can I write this equation as V by R is equal to R? Am I right or not? V by I is equal to R. Okay, see, this value of R depends upon the nature of the material. I mean, whatever the material you have considered as a conductor, it will always, the resistance will always depend upon the whatever the material you used. Okay, and also depends on its temperature. Okay, but it does not depend on the whatever the value present over here, that is whatever the v or I, it will not depend on these two terms, but it will always depends on the material you used as a conductor and also the temperature you are applying to that conductor. So this is all about the Ohm's law. Okay, so coming to the, so whatever present here, see the mathematical Ohm's law I have derived, that is V is equal to IR, where R is the constant of proportionality called as the resistance of the conductor. So we have R is equal to V by I. The SI unit of resistance that is denoted by the SI unit, that is ohm. Ohm. Okay, 1 ohm is equal to 1 volt per ampere. Okay, 1 ohm is equal to 1 volt per ampere. So the dimensional formula, that is equal to I to the power of minus 2 m into L square into T to the power of minus 3. Point to be remember. So now at a given temperature, at a given temperature, suppose if you consider any conductor that is which is having the length L over the area that is A, over the area that is A, so that R, okay, whatever the resistance is directly proportional to the L divided by A, the length of that conductor to the whole area. Or R is equal to, if I want to remove the proportionality constant, that is rho into L by A, that will become rho into L by A. So where rho is equal to specific resistance, or the, which is also equal to the specific resistance or the resistivity of the material. This is also equal to the resistivity of the material of the conductor. So where rho is equal to, where rho is equal to m divided by n e square into tau. This is the this is the resistance or resistivity of the material. So L by as it is. Okay, whereas rho is equal to m divided by n e square into tau. So where rho is the specific resistance of the material, and for a conductor of a length L which is having the circular cross section, this is the circular cross section from front part to the last part. Okay, it is given by the resistance of the conductor, that is R is equal to rho into L as it is divided by pi AB. Here the radius of the cross section varies linearly from point A to B. So they have shown you here the surface, whatever the half surface, I mean radius of that circular ends, that is A which is smaller at the starting point, but B which is bigger one. So therefore for a conductor the length L having a circular cross section, the resistance of the conductor is R. Okay, the resistance of the conductor is, it is R. Here the radius of the cross section varies from the point A to B, that is B minus A is less than or equal, less than length of the, okay, whatever the surface at A and B are, those are less than the total length of that conductor. Okay, that's why I have written like this. So this is all about the Ohm's law. Okay, now coming to the point, I have said you the resistivity or specific resistance. So let us learn this in complete manner. Okay, in detail, resistivity or specific resistance rho. See, it is defined as a numerically equal to the resistance. It is equal to the resistance across the opposite faces of the cube of the given material of unit length and unit area of the cross section. So if you consider the mathematical expression here, so according to this only the statement I have derived here. See, if you see the derivation, the resistivity of a material, okay, it is defined as a numerically equal to the resistance across the opposite faces of the cube of the given material of the unit length L and a unit cross section area. Okay, on combining these three, combining these three terms, In the given equation, we will write as resistivity or specific resistance is equal to the capital R into A divided by L, where R is the resistance, A is the unit area of cross section, L is the unit length. Okay, unit length. So R is in ohm, R it is in denoted by the SI unit, that is ohm. A is in square meter area. Okay, L is in meter. So if you substitute the SI unit of rho, it is a ohm meter. It is a ohm meter. So what is the SI unit of resistance here? Only ohm. But SI unit of resistivity or specific resistance, it is ohm meter. Please don't forget it. Okay, the SI unit of resistance, it is only ohm. Okay, if you come to the SI unit of rho, that is resistivity or specific resistance, rho, that is equal to ohm meter. So if you come to the dimensional formula for rho, that is equal to I to the power of minus 2 m into L to the power of 3 into T to the power of minus 3. Okay, the resistivity of the material is related to the microscopic quantity. If you consider the microscopic quantities by the relation, that is rho is equal to small m divided by n, number of electrons per unit time, and whatever the electrons present inside the conductor, E, and tau is a relaxation time. This is a resistivity of a material related to microscopic quantities. Now, the resistivity of a conductor, which will always depends on the nature of the material as well as the temperature. I have said you. Okay, the resistance of the material also depends on the nature of the material. I have said you, the material whatever you use as a conductor, it also depends on the temperature. Okay, it is also depends on the temperature, the material, and also the temperature you apply to that conductor. Okay, this is all about the resistivity. Now, another point to remember, that is these are the properties of, these are some conditions. Okay, some factors. So whatever the factors affecting on that resistivity, first thing is resistivity of a conductor. This is first thing. These are the factors. The resistivity of a conductor depends on the nature of the material and the temperature. Okay, and now the resistivity is independent of the second one, that is resistivity of the material, that is independent of physical dimensions. What are those physical dimensions? Size and shape of the conductor. See, if you consider any kind of material which may be in different shape or size. Okay, these are also conductors. Okay, if you consider any conductor which in any form, which is any size, so this resistivity will not matter at all, because it is independent. Okay, it is independent of the physical dimensions, that is size, that is size and shape. Okay, size and shape of the conductor, but its value is different for different materials. Okay, so if the size and shape are different, its value is also different. Okay, the resistivity of the resistivity of that material is also different. Is it or not? That's why it is, the resistivity is independent of the physical dimensions. Those are size and shape of that conductor. So if the size and shape of the conductor is different, its value is also different for different materials. Is it or not? Okay, its value is also different. So this is one property, and this is also one factor. Now the third factor, that is good conductors have low resistivity. Okay, while insulators have very high resistivity. Let me clear you something here. Say the good conductors. What are good conductors? Which allow the electricity to pass through them easily. Whatever the conductors you consider which allow the electricity to pass through them easily, those are called as conductors. These are the good conductors which are having the low resistivity. See, the capability to flow of electrons inside that good conductors is high, but the low resistivity, the opposition to the flow of electricity in case of good conductors is different. In opposite, the resistivity will be low. Of course, it is low because conductors means it is having the good capability to pass the free electrons inside that conductor. That's why it is having the low resistivity. So while if consider the insulators, what are insulators? That will not conduct any type of electricity, that is having the less capability to pass the electrons inside that conductor. Those are called as a insulators, which are having the very high resistivity. Why? Because these will resist the flow of electricity inside the conductor. Those are called as the insulators. So that's why it is having the very high resistivity. Now coming to the semiconductors. Okay, now coming to the semiconductors which have very high resistivity, whose resistivity which will lies between that of good conductors and insulators. I mean 50-50. It may conduct or it may not conduct. Okay, it will always, the property of the semiconductor will always lies in between good conductors as well as insulators. So those conductors are called as a semiconductors. So the semiconductor materials having the property in between the good conductors and insulators, those value, the resistivity will also lying between that of the good conductors and the insulators. Okay, the resistivity will also lies in between the conductors and insulators. Okay, this is the third factor. Now coming to the fourth factor. So alloys, whatever the alloys, if you consider, have resistivity which is greater than the resistivity of its constituent metals. Okay, as coming to the alloys and metals, the the resistivity for alloys, okay, the resistivity of alloys will always be greater than the resistivity of the constituent metals, the resistivity of the constituent metals. So if you consider two, if you compare the two resistivity of the two materials, one for alloys and one for metals, the resistivity will always be higher in case of alloys, which will be low in case of the metals. So this is all about the resistivity. This is all about the resistivity. So dear students, in today's session, I have discussed about current density. So what are the important concepts related to the current density, important factors, and drift velocity. What do you mean by drift velocity? What are free electrons? How the phenomenon will happen here? So this is all about the drift velocity of the free electrons. So if you consider the drift velocity, there will be some collision between the ions. So the total time, the average time taken for the successive collision of the ions is called as a relaxation time. Okay, this is called as a relaxation time. What is mean free path? Now, as coming to the mobility, I have discussed what do you mean by mobility, and if you consider in case of semiconductors what will happen. So now if you consider the expression for current and current density, that is in terms of the drift velocity Vd, so how it will vary, and also the most important concept for 5 marks, that is Ohm's law. They may ask for 3 marks, or they may ask for 2 marks, or they may ask for 5 marks. So whatever the important phenomenon present in the Ohm's law we have discussed. And if I the what in case of resistance, how the resistivity will come, and or a specific resistivity or specific resistance, that is denoted by the rho, and what are the factors, whatever the factors related to that resistivity we have learned in this session. So I hope this whatever the concept I have told you in this session are clear to you. So dear students, please don't forget to subscribe our channel, and please learn things in a clear manner. Don't be confused. So whatever the concept I have said in this session, please learn more, and please learn the concept, understand the concept I have said you clearly. So please take a note of wherever I have said you, and make a notes. And if you go on reading that notes, whatever I have shown in the slide, so please note down it and make a short note, like which will help you in the examination part of time. So I hope this session is clear to you. So by saying this, I would like to wind up the session for today itself. And in the next session, whatever the concept related to your syllabus, I'll go on discussing. So it will help you with one or the other way. So thank you, dear students.